Hello and welcome to FlexPDE topic number 9, torsional elasticity twisting. This is our final elasticity topic, and it deals with the remaining moment that we haven't dealt with yet. So we've already dealt with axial stress leading to normal deformations and shear stress leading to shear deformations, but what if we have axial stress gradients and equivalent bending moments from that? So axial stress gradients leading to bending moments lead to flexure. That's what we dealt with last week. The last thing is shear stress gradients, which cause twisting moments. So a moment which is not in a direction perpendicular to the beam axis, so maybe like a moment in the z direction causing bending in the y direction on the x surface, or a moment in the y direction causing bending in the z direction on the x surface, but a moment in the x direction on the x surface which causes twisting. So this is what we're going to be dealing with this week. Torsion turns out to be parallel to a lot of the other things that we've dealt with so far. So normal stress is the force perpendicular to the surface divided by the area of that surface, and this leads to a normal strain, which is the rate of change of the, let's say, x displacement per step in x, and leads to a Hooke's law that stress is related to the strain via the Young's modulus. For shear, we said that the parallel force divided by the area of the surface is the shear stress, at least in a local sense. You might have to turn this into a derivative to get the local shear stress, and that leads to a shear strain, which is the sum of these two displacements in perpendicular direction. So del u by del y plus del v by del x, the x displacement per step in y plus the y displacement per step in x tells you how the planes are kind of sliding towards each other and going from squares to parallelograms. That's the shear displacement, and the shear strain is related to shear stress via the shear modulus G. So flexion, bending, is what we dealt with all last week, and there we said that the moment is equal to EI, flexural rigidity, usually left those coupled, times the curvature, where curvature is related to the second derivative of the transverse displacement per step in the longitudinal direction. This week, we're going to see twisting deformations, which are torques divided by torsion modulus, related to the second moment of area in bending. And that thing is going to be related via the shear modulus, because again, this is like a shear phenomenon, twisting, unlike bending, which is a normal stress or axial stress gradient phenomenon. So related to shear modulus to the torsional strain, which is the new angle that the thing has that is twisted through, the angle it's twisted through per step in length. So this is the torsional strain, in the same way that curvature is like the bending strain, and the relationship between the torsional strain and the torsional stress is the shear modulus. So then, to get a little bit more systematic and show some diagrams of this, if we have a beam extending in Z, then the moment about the z-axis, moment in the z direction, will cause a twisting of this beam. So it makes the thing go from what was originally this dashed line to this new solid line right there. So it builds up an angle that depends on the position. At the end here, you might, we've labeled this alpha. You might say that it's like theta at LZ. If this is the final part of the beam, this could also just be some cross section through the beam. Anyway, the moment is going to linearly relate to the slope in angle per step in Z, the torsional strain effectively, via, just like EI, we've got GJ, right? Where J is now the torsion constant, and we'll figure out what that is, and G is the shear modulus. So together, not surprisingly, GJ is called the torsional rigidity, just like EI was the flexural rigidity. So if there's no warping, if this cross-section remains in exactly the same shape and just sort of twists around, then the shear stress and strain are going to increase linearly with distance from the rotation axis. So the angle is a constant, but because of how arc length works, that means that the farther away points have moved by more. So they experience more shear strain, and the shear strain that they experience is proportional to the shear stress via the shear modulus. So let's look at this. The little bit of slope in angle is the extra little bit of twist that has happened from one step in Z, right? So per step in Z, we've got an extra little bit of twist, del theta by del Z, and then you multiply that by whatever radius we're at inside the beam, r, and that's going to tell you the extra little bit of displacement you have there, which is the shear strain. So this thing is, kind of think moving in the Z direction per step in the Z at some r. It's the extra little bit of shear strain compared to the piece of shear displacement compared to the piece just before it. So that's the shear strain. It's the shear displacement per step in Z. So this thing is, after you substitute in how shear strain is related to shear stress, we can have it as the shear stresses divided by the shear modulus. And so this means that the shear stress itself is going to be scaling out linearly with step in r. Another way to look at this is just look at this cross section here. You've got the pieces in the middle have not really moved that much, but the pieces near the edge have had to move a lot. So they're experiencing more strain linearly out with distance r from the center, and therefore they're going to have more stress as well. The places right on the surface are going to have the largest shear stress and largest shear strain to make this twisting happen. Think of it like this. This line here, from one point to the end, after it twists on the outer surface, has to go to a slope that's kind of down like that. It's moved this much, right? The arc length of this thing divided by the original length is going to tell you how much the shear strain was, right? So we've got this step, the displacement in this direction, divided by the original length is the shear strain, in the same way that an axial strain would be the displacement in the length direction divided by the original length. And this distance is going to be larger depending on what r you're at. So the places near the center are not going to have nearly as much of a step there, so they have much less shear strain and much less shear stress. So from this relationship, you can work out what the magnitude of the stress is here and say that that's equal to G times R del theta by del Z. And then if you substitute in the del theta by del Z that we had from our Hooke's law for torsion, you can relate this to the torsional moment divided by the torsion constant. So the stress just scales up linearly. As we increase the moment we're applying, we're going to get more stress on the surface. As we increase the radius we're looking at, the radius of the spot within this cross-section we're looking at, we get more shear stress. And as we increase the torsional constant, the resistance to rotation from the geometry perspective, we get less shear stress. The actual torsional displacement that we get, the strain that shows up, is going to be dependent on also the shear modulus, but the stress doesn't depend on that. The stress is going to be higher if you have higher moment and you have lower torsion constant, but the strain is going to be also affected by those things, increasing with more moment, decreasing with more torsion constant, but then also decreasing with more shear modulus. For a circle, the torsion constant ends up being exactly the second moment of area around that cross-section. So this is similar to that moment of inertia, that I calculation, the second moment of area we had for bending, except the axis is out of the page, so we have to use r squared. But it also turns out that this is only true for torsion if the cross-section is a circle. If the cross-section is some other shape, like a square, it ends up being not exactly the thing you would calculate using second moment of area. It's not just that the integral is more difficult when you have a non-circular cross-section, it's that you have warping in non-circular cross-sections. So if it's not a circle or like a ring, which is a circle with part of the circle missing, then you need to use experiments or maybe numerical methods like FlexPDE to figure out what the actual torsion constant is for that cross-section. So in this example, we're going to compare the second moment of area of a square and circular cross-section with the torsion constant. So if we have a circular cross-section, then we can find out what the second moment of area would be by just integrating the square of the distance away from that axis over that cross-section, right? So let's integrate r squared with respect to area. So how do we integrate with respect to area if we have a circle? Well, in polar coordinates, this is pretty easy. The integral is going to be integrating r dr d theta. From r goes from 0 to big R, and theta goes from 0 to 2 times pi. So we need to do two integrals, and the thing that we're integrating, the integrand, is the function times r with respect to r over that range, and with respect to theta over that range. So here we go. We get r to the 4 times pi by 2, and that's exactly what we got for the torsion constant. What about for a square? For a square, we will have, again, a double integral, except now, with the bounds being rectangular, it's a lot less convenient to use polar coordinates. So we better just go x equals, let's say, square of side length 2a. Notice that a is half the side length, so we're going to go x from negative a to a, and y equals negative a to a. But we have to put in what r is. So now let's say that r is equal to the square root of x squared plus y squared, and then work out that integral. And we have 8/3 a to the 4. Let's evaluate what that is. 2.67 a to the 4 is what the second moment of area would be. But actually, if you find the torsion constant, you see that it's not quite that high. It's 2.25 a to the 4. So, in fact, a square cross-section is easier to twist around than you would predict by the second moment of area. The reason is you take this square cross-section, and the second moment of area would say what has to happen if none of if it can't warp, if it can't move up or down in different things and kind of like wrinkle, but it can do that. For a circle, it doesn't help, right? That just adds strain. But for a square cross-section in twisting, that can actually relieve strain. So it has this method to twist around that ends up taking less energy than you would predict using just the second moment of area. And that's why the torsion constant for a non-circular cross-section is always going to end up being a little bit lower than you would have predicted with the second moment of area. So next up, if we want to compare what we're getting in Maple to Flex and see things working out nicely, the first step is to learn how to draw circles in FlexPDE. So this is not a very deep physics concept, it's just a syntax thing. And the way to do this is using the arc command. So we'll start at some point, and then rather than using line 2, we can use this thing, arc, say what the center is, and then give it an angle. So why don't we use the practice problem code from topic 8 that we did before, that was in the most recent video before this one, and modify it. So instead of this thing, we are going to have a circle. So we'll say start 0, 0. We don't need to apply any boundary conditions. We'll just leave it at the default load UVW is equal to 0. And then we'll say arc center with the more sensical phonetic American spelling of that compared to our native Canadian. This is from a time when the U.S. looked at things and said, you know what, this spelling center like this doesn't make sense. It's backwards and non-intuitive the way you pronounce things in English generally. So let's say that that word should be spelled like this. What a time it was. This is, I guess times have changed quite a bit if they are not taking more steps to adopt the metric system since then. Anyway, so here's our angle. We've got start 0, 0 and an arc with a center of 0, 0, angle of this. Now wait a minute, we were at point 0, 0, so that's not going to work. This is going to make an arc with no actual radius. So what we could do is arc from 0, 0 around a center that's displaced, like maybe LX 0, and that'll draw a circle. So what this has done is it started at 0, 0, and then it made an arc with a center of that arc at LX 0. So it should have a length across it of 2 LX. Let's check. LX was 0.5. So we're going to be going on these plots versus X from 0 to 1, and from Y is negative 0.5 to 0.5. Kind of neat that it'll still calculate this bending stuff that we were doing. This is just bending under its weight, no problem. What else could we do? We could start it at LX 0 and then make an arc with a center of 0, 0, and this should be exactly the same thing. This is starting at the point actually this is going to sort of be this one is centered at 0, 0, of course, because we put center at 0, 0. It still makes the same shape, but now the graph is centered both in X. We started at this point, and then we said do an arc with a center of 0, 0, and draw that circle. You don't have to do a 360-degree arc. You could do a 180-degree arc. This is going to show us whether it draws in the counterclockwise direction or the clockwise direction. Let's find out. Let's edit. We made a mistake. We have to, after that arc, go line to close it off. All right, so it looks like it draws in the counterclockwise direction first, because we have just the top part of this, and then line to close. The same code will solve this thing out. So in case you want to know how, this is kind of neat with finite element methods. Although we're just working on simple examples that we can compare with Maple, there's no reason you can't take a more complicated geometry and draw that and see how things work. So one question is the displacement going to be more in this direction if you put the wider part on the top or the bottom? Does it matter? Let's see. It looks like we've got a displacement of 3.7 E minus 4. What if we did an angle of negative 180 degrees to map out, to kind of have this thing upside down? It moves 1 E minus 3. It looks like it displaces, at least at the point that we're considering, more under its own weight if we put the arc part on the bottom rather than the top. And that's kind of interesting. Does it have to do with whether it was fixed in X at the back surface? Perhaps. 1.02. And what if we took this positive arc again? 3.7 E minus 4. That's so much of a difference that it doesn't make sense. And the reason is because actually in this problem we had different material parameters and density depending on if Y was larger or smaller than the Ly by 2. So we made the material that was at low Y values less stiff and heavier than the material that was at high Y values. That material was more stiff and lighter. So that's the reason behind this bending. If we just stuck with the same material all the way through, then we wouldn't have had any more of those extreme differences from the top and bottom. So now we've got 1.03 when it's on top, and if we made the arc go the other way, we would get 1.02. Slightly more resistance, it looks like, when we've got the arc bending on the bottom. Okay, anyway, that's bending, and that's how you draw circles with FlexPDE. So the next step is to relate the twist angle that shows up in a beam and the slope of the twist angle to coordinate displacements and strain. So coordinate displacements, the U and V, displacement in X and Y on this surface, and the strains, so the shear strain that's showing up. And using this and the Hooke's law that we already had for strain, we're going to be able to derive this Hooke's law for torsion that we've been mentioning, and we're going to know how to relate twist angle to the X and Y displacements, U and V, so that we can determine what the twist angle that we're getting from a thing in FlexPDE is from a simulation in FlexPDE and compare that with what we're calculating in Maple. So first up, if we have a point that is at position x and y in Cartesian coordinates and r phi in polar coordinates, we're going to use theta for the twist angle, so we'll use phi as the polar coordinate variable. Then x and y are related to r and phi via these relations that you probably are familiar with from polar coordinates. So x is r cos phi and y is r sin phi. And if you want to go the other way, then r is the root of x squared plus y squared, and phi is the a tan 2 of y and x. A tan 2 is a function that you have in a lot of computer programming languages that tells you what that does arctan of y over x, but then also keeps track of the sine of x. So if you go into FlexPDE, for example, and you say, I think we can just do this, report atan of 3 over 2. Oh, arctan? Arctan 3 over 2, okay. Sometimes it's atan, sometimes it's arctan. There we go. What about if we have the arctan of negative 3 over 2 and the arctan of 3 over negative 2? So let's see, 3 over 2 would mean y is 3, x is 2. So we have some angle that's up a little bit more than 45 degrees, or a little bit more than pi by 4. So this arctan of 3 over 2 is this positive number. Arctan negative 3 over 2, if y is negative, we expect like a negative angle there. But arctan of 3 over negative 2, if this meant y is 3 and x is negative 2, then we should have this kind of bigger angle over there. The problem is arctan only has 180 degree, so tan has 180 degree periodicity, which means arctan will always give you an angle between negative pi by 2 and positive pi by 2. And you need to correct it to the angle you actually meant if it was in quadrants 2 or 3, the negative x ones. So you could do this by manually saying, was the denominator negative? Then actually what I meant is this plus pi to get the correct angle. So 2.15 is the one we wanted. Or you could use the arctan 2 function. Let's see, is it a tan 2 in FlexPDE? 3, negative 2? Yes. So a tan 2 will keep track of what was the sine of y and the sine of x, which is lost when you just divide those two numbers, and then automatically give you the right angle. So this is the same as arctan, negative 3 and 2 of the first argument over the second argument. Sometimes it gives you one that is, it looks like arctan 2 in Flex is always going to give you a number that is positive, but this angle here should be the same as the arctan we got here plus 2 pi. So remember, if we add pi, then we're not getting the same angle. We've got one on the other side, but if you add 2 pi, then that will be the same angle. Okay. And there's nothing really special about FlexPDE with regards to a tan 2. You have this in a bunch of programming languages and computer programs. So here is here's an interpretation in Excel. So we can say a tan of y over x and get what those arctans are. And as you can see, it gives you the same thing, whether y was negative or x was negative, because that information is lost when you just divide those two. But a tan 2 will keep that. We'll keep track of that. Now be careful which order it expects the arguments in. So the programmers of Excel have decided that the first argument should be the original x value, and the second argument should be the original y value. As you can see, that's not uniform among other things. So FlexPDE has decided that the first argument should be the y value and the second one should be the x value. In addition, Excel has decided that it's going to give you an answer for arctan 2 that agrees with arctan when you are in quadrant 4? What about if you are in quadrant 3? So we've got both things negative. Then it gives you a negative number here. So FlexPDE's version is always giving you a number in the range of 0 to 2 pi for arctan 2, whereas Excel is giving you a range in negative pi to pi. So always test out how the arctan 2 function is implemented in the particular programming language that you're going to use before you go off and use it. Here in this setup, I'm assuming that it's the version where the first argument is y and the second argument is x. So that way, this is going to be the arctan of y over x, which is what you would get after you divide the first one by the second one. So if we have some rotation, then the angle that it was at in polar coordinates has moved from angle phi to angle phi plus theta. If there's no warping, then the r stays the same if it's rotating about the origin. So let's imagine that it's rotating about the origin, and that means the displacement will be in x, the new x coordinate minus the original one, and the new one is r prime cos phi prime minus r cos phi, but the r's stay the same. So this is just r times the cos of the new angle, phi plus theta, minus the cos of the original angle. And then same thing in the y displacement, except with signs inside. Now, if there's no warping, that means that the z displacement is 0. If we're in pure twisting, we don't have any z displacement, so the change in z displacement per change in the plane is 0. We don't have any of these w's showing up, and that means the shear strains on z in x and z in y, which are given by these partial derivative sums, are going to only involve changes in u with step in z and v with step in z. So the x displacement can change as we move further along this beam and the twist angle gets larger, but the z displacements will not change with position within each of these cross sections. So they won't change with x and y if we have no warping. And that means that the strains, which we know are related to these stresses, the shear stresses divided by the shear moduli, are going to be just manifested by slopes of x and y displacement per step in z. If we then substitute in these x and y displacements that we calculated into these formulas, then the offsets are going to go away, right? When we take the derivatives of these things with respect to z, the r value that we're talking about and the phi value that we were at doesn't change. These are original coordinates, right? These will not change with z, but the twist angle can change with z. So we end up with just this. Derivative of cos is negative sine, so negative r sine theta plus phi d theta by dz. And then for the, that's the zx shear stress that's equal to that, and the zy shear stress will be r cos. Once you differentiate the sine, we'll take r cos theta plus phi d theta by dz. So this shear stress is going to be leading to a torque about the center, which is given by this integral. We're going to integrate the x position. Let's go over here. So the x position times the stress in the y direction will create a positive torque about z, and the x stress times the negative y position will also create a positive torque about z. We have a picture of that down here. So the further down you go, the more the stress to the right will create a torque about the center, and the further right you go, the more the stress up will create a torque about the center. This one's in different coordinates. This is a YZ plane with X out rather than XY, but you get the idea. So it's the same idea. The more to the right we go, the more the upward stress will create a positive torque, and the more down we go, the more the rightward stress will create a positive torque. So substituting in these stresses that we just calculated, we can clean this up, and we end up with the following. Where does this come from? Let's have a look. We've got a d sigma by dz in each term that we can pull out. We've got a g in each term. Oh, wait a minute. We're supposed to have a g in each term. I substituted this in incorrectly. So there's a g here as well in this in this first term after we take the g up there, tau zx. And so the g and the d theta by dz gets pulled out of that. I guess we can leave the g inside in case it's not the same over the cross section. And then what do we have left after we do that? We've got an x r cos theta plus phi, and we've got a y r sine theta plus phi. Now, if theta plus phi is basically theta, so we have sort of a small twist angle, then the cos of theta plus phi is just cos of phi, and r cos phi is x, right? So this thing is going to be an x squared. And same thing over here, with the negatives cancel out, we've got an r sine phi, and that's y. So this is approximately equal to just the x squared plus y squared times g dA del theta by del z. Again, this relied on us being able to say that there was no twisting to say that the shear stresses were equal to just the slopes in the x per step in z and y per step in z for those shear stresses, rather than the w displacement, the z displacement there. And as long as that's the case, then we do find out that we have exactly the second moment of area that's relating the g times shear strain, torsional strain, shear modulus times torsional strain d theta by dz to the applied moment. So let's kind of put that in. We've got then mz is approximately equal to what we have here, which is the integral, the integral of r squared dA over the area times g del theta by del z, which equals jt g del theta by del z, at least as long as there's no warping. So another thing that is useful here is the ability to figure out what the twist angle that occurred was. So besides deriving this thing, which we already knew, maybe you just didn't believe it before, but now we've got this derivation of this, and you see the steps that went into making this happen, we needed to have a small angle for this to be exactly the torsion constant that's showing up inside there, for this torsion constant to be the second moment of area. And we also needed the shear modulus to be constant across the cross section to be able to take that out of the integral, and we needed all the displacements to be just in the x and y direction on this plane and have no z displacement coming from the shear stresses on the z cross section. Besides that derivation, another thing that we're in a position to do right now is figure out how the angle, the twist angle, is related to deformation things. So from the ratio of y prime and x prime being the tangent of theta plus phi, where does this come from? That comes from the final position specifications here. So once you know if the final position is this at phi plus theta of an angle, then you can just use an arctan 2 to figure out what that angle has to be. So if you know the original angle, if you know the angle before deformation, and you call that phi, and you know the angle, and you know the position after deformation, then you can figure out the final angle. This is something we can do in FlexPDE. So we could define theta as a tan 2 of y and x, and then define x prime as x plus u and y prime as x plus v, as y plus v. All of these things we would know, and therefore figure out what theta is by taking a tan 2 of x prime, y prime, x prime, and subtracting the original phi that we had. So this is going to be our method in FlexPDE. Just before leaving this section, it's also possible to get a little bit of intuition about how these displacements will be related to twist angle for small twist angles. And let's go back to these displacement formulas that we had up here and imagine that the twist angle is small enough that we can say that cos of theta is 1 and sine of theta is theta. If we do that by using a sum angle formula, saying cos of phi plus theta is cos phi cos theta minus sine phi sine theta, and sine of phi plus theta is sine phi cos theta plus cos phi sine theta. Did I say that right? Sine, cosine, cosine, sine, right? Sine of theta, yeah, okay. Sine, cosine, cosine, sine. There we go. We got it. We wrote it in sort of the opposite order there, but it's the same thing. So once you expand these out using the sum angle formulas, you can turn the cos thetas into 1, and then the sine of phi here will cancel with the sine of phi, and the cos of phi here will cancel with that one. So you're left with just negative r sine phi theta, and r sine phi was the y position. So this means the x displacement that happens after rotation is negative the y position. The more down you are for a small angle, the more the x displacement is going to be. The amount that you move to the right is based on how far down you were, or the amount that you move to the left is based on how far up the point was for a small displacement. What about the y displacement? This ends up being just r cos phi times theta, so that is just x times theta. So the amount up you move is how far you were to the right. Points to the left will move down based on how far they were to the left, and points that are to the right will move up based on how far they were to the right, at least for small angles. Let's do a torsion beam example. So now that we've got all this theory worked out, we can try to do some work in Maple and FlexPDE and see if we can get them to agree or see where they disagree. So a beam is centered on the z-axis, meaning z is going to go along through the center of the cross-section with this Young's modulus, 5 gigapascals, this Poisson's ratio, and this total length in z. It's also fixed on its z equals 0 surface and is subjected to a torsional shear stress on its z equals Lz surface that's given by this formula. So we have a stress on z in the x direction, which is based on the negative y position, 1 megapascal per meter. That's going to make it in megapascals after we multiply by the y position, and a stress on z in the y direction, which is given by this expression, x times 1 megapascal per meter. So the more to the right we are, the more upward stress we have. The more down we are, the more rightward stress we have. So these will create torsional stress. Stress that these together are both stresses that cause a torsional moment in the counterclockwise direction on that xy surface. So in the positive z direction on that xy surface. Now, we're going to do this for a circle with a 1 meter diameter and a square with a 1 meter side length, both centered on the z-axis. Now, we can figure out the twist angle in Maple using the relationships that we had before by saying that the twist angle d theta by dz is going to be a constant all along the length if we're in pure torsion. And since we've got this fixed torsional stress on the final surface, we should be in pure torsion. So that means that we'll be able to say that theta end is, well, actually theta is going to be the integral of d theta by dz, d theta by dz, from z is 0 to z. And we can figure out theta end by saying subs z equals Lz into theta. Right. So d theta by dz will actually end up being a constant, so it's just going to be this thing times z once we figured out what it is, and then we'll just have that multiplied by Lz to get the angle at the end of it, the twist angle that results at the end of the beam, but also the twist angle that results at any cross-section along the beam, the amount that that thing has twisted compared to the start. So how do we figure out this d theta by dz? Well, that d theta by dz from this formula is equal to mz over jt times g. And jt times g we can get from the table up here. For a circular cross-section, jt will be equal to, let's do the circle. Maybe we'll put that up here. jt is equal to pi by 2 times the radius of the circle to the power of 4. And g we can figure out from the Young's modulus for this thing. So the Young's modulus is 5 and the Poisson ratio 0.2. Let's put that in here. E is equal to 5e9, nu is equal to 0.3, not 0.2, and Lz is equal to 4. Then g is equal to E over 2 times 1 plus nu. And that should give us JTG, all good. So we need to know what the moment is, and we need to know what the radius is for this. If we have a 1 meter diameter, then we've got R is equal to 1 over 2. And there we have it. So all we need now is what that moment is, and we can figure out what this would be for that circle. Now, what actually is this? The thing that makes this, what's going to be different about this for the circle? It's really just this JT and R stuff, right? So maybe we'll go and put this shear modulus up there. That's going to be the same every time. And the R and JT is what's specific to this for the circle. When we have this for the rectangular cross-section, we'll have exactly the same thing, but we will use a different thing here. So for the rectangular one, we will say that we have a side length of 1 meter. So maybe we'll say Lx is equal to 1. And that means that JT for a square is going to be 2.25 times the half side length to the power of 4. So this is the square. And we expect that the square is going to be harder to rotate because the circle is contained within the square for this thing. So a 1 meter diameter circle is totally contained within the square. Now, how much do these extra corners make of a difference? Let's see. We can evaluate this. Instead of pi, we can use 3.14159 to force it into a floating point. So it looks like it makes quite a bit of difference by having that extra stuff at the edges. Similar to bending, for torsion, because of this kind of R squared stuff in the second moment of area around the center, even though the warping finds a different way to deal with that, the extra distance away from the center ends up making a fair bit of extra resistance to twisting. You can see it goes like R to the power of 4. So the bigger the radius, the much more resistance to twisting we have. So it's not so surprising that the extra little bits of edge that exist around the edge of the square cross-section compared to the circle end up leading to a lot of twisting resistance. So all we have to do now to figure out what the angle is figure out how to relate this shear stress distribution to a twist angle. And that we can do by taking a cross product at the end here. With linear algebra, going back to the week 3 stuff, we'll say that at some point on the surface, let's say R is equal to xy 0, we've got no displacement in z, so some point on the surface about the z-axis, we are going to have a little bit of force, dF, from our little bit of stress on that surface, which is given by, let's say the stress times dA. And the stress is equal to tau z in the x, tau on z in the y, and 0 because we don't have any stress on z in the z direction. That would be sigma, maybe sigma z or sigma on z in the z if you want to put two subscripts on that. So here we go. Next, we can take the net force and take the R and cross product that with the net force to see what kind of torque we're going to get. So torque, maybe d torque, is going to be equal to R. Remember, cross product is like that, with that little bit of force. So you see, because we're not displaced at all in Z, we have the Z-directed stress creating torques in the X and Y direction on this surface. That's what we were dealing with last week. Remember, the axial stress creating these moments on that surface. So the stress in the Z direction creating bending moments. But the twisting moment, the moment about the Z-axis itself, comes from those shear stresses. Yeah? So for the shear stress distribution that we're given, tau Zx is equal to negative y times 1e6, and tau Zy is equal to x times 1e6, we can work out what the stress is in that direction. It looks like it's a large number x squared and large number y squared ends up being a totally positive definite moment that's created in the z direction there. So let's see. We'll say that there's no stress applied in the z direction, and then we got rid of those first two moments, and what we're looking for would be dmz is equal to d torque, third component. So just the one in the z direction. We could have kind of worked this out manually here and said, hey, you know, it's a cross product R cross df, which is xy0 crossed with just the shear stresses that we have applied because there's no axial stress. And this is what gives us, hey, it's the distance to the right times tau z in the y minus the distance up, or plus the distance down, times tau z in x, like we were working out before. So anyway, this is our little bit of moment per little space dA. What if we want the total moment? Well, mz would be equal to dmz by dA, just get rid of that little dA, and then integrate that over the whole surface. So we'll integrate this from y equals, let's see, negative Ly over 2 to Ly over 2, and from x equals negative Lx over 2 to Lx over 2. And Lx and Ly are actually the same in this situation. Lx is that, Ly is also equal to 1, and there we go. We should have the total moment by just integrating the little bit of moment per step in area that we found with respect to area over the whole surface. And we have a moment of 166.7 kilonewton meters. So we had, let's see, this amount that was in pascals per meter, and we multiplied it by meters to the power of 4. So Pascal per meter is Newton per meter cubed. Multiplying it by meters to the power of 4, we'll get Newton meters, as we should for a moment. That was the last piece. Now that we have that moment figured out, the rest of the code that we worked out has found out what the angle should be at the end for the square, and we can figure out what it would be for the circle by modifying things a little bit and making the, I guess we have to mess with it a bit and make the integral apply over the circular cross-section, changing the boundaries a little bit. Let's work that out. So we'll put in here just the one for the circle, and we'll make this one just the one for the square down here. So how do we do the one for the circle? Well, what we need to do is change the boundaries from this range on y and this range on x to the range that's going to give us a circle. So the circle can be defined as the range from negative, from y equals negative square root of r squared, let's see, minus x squared to positive root that, right? Because the bottom curve of the circle is the line where y squared plus x squared, we've got a circle centered at the origin conveniently, so it's easy to write that. Y squared plus x squared is equal to r squared. And so we're going to go from negative root that to positive root that to go across the bottom and top of the circle. Once we've done that, we just need to take x over its extreme value. So x goes just negative r to positive r, because we've already incorporated the fact that that it doesn't need to go all the way to the ends of the ranges depending on what y is by bringing in the y boundary. Right, so now we should have something that gives us a moment, and the moment should not be as big as the moment was last time because we don't have as much of that area as we did before. The twist angle that we get for this one is actually lower because the moment seems to have reduced by more than the torsion constant reduced by. So the square cross-section, we had 0.14 for the torsion constant and a moment of 167,000 Newton meters. And the torsion constant for the circular cross-section is about 0.1 and about 100,000 Newton meters. Let's see what we get in FlexPDE. So we are going to go back to the calculation here, the problem statement, problem definition up here, and we're going to say this is topic 9, maybe example e.g. 9131, and save a copy of this, torsional elasticity e.g. 9131, and then put in the dimensions. So let's say Lx is equal to 0.5, Ly is 0.5, and first let's do the circle. R is equal to, so maybe, R out is, oh, I guess actually we have this already. R out is just 0.5. Yeah, and it's 4 meters long. What else do we have? We've got Young's modulus, which is 5 gigapascals this time. And nu is 0.3. We don't need any of this density stuff, and we better get rid of that in our differential equation. We are drawing a circle that has a radius of Lx and is centered at 0, 0, so that's good. Oh, this wasn't a complete circle. Let's go, angle is 360 degrees, and now we should be getting that complete circle. Let's see. Right, we took away the weight, so now there's no stress making this move at all. We've got just no actual displacement. Still doing those arctan calculations we were doing at the end. We don't need that. Right. So what can we do? How can we apply the torsional stress that we're interested in? Well, we need to apply a stress on the top surface, which is in the x direction given by this. So load U is equal to negative y times 1e6. And we need a stress in the y direction given by this. Load V is positive x times 1e6. So this should be giving us that twist angle. Kind of expands out, and you see we've got some interesting twisting stuff here. So Flex is overemphasizing how much this top surface is going to be changing in size compared to the twisting, because we're applying stresses out, and as soon as it twists a bit, that is kind of pulling the things apart because of the direction that we're applying the stress in. So if we don't allow the stress direction to change as the thing rotates, then it's also going to be pulling it out a bit, but hopefully that's not much of the displacement and it's not going to change the way we're calculating the angle. Let's calculate that angle. So first thing I want to do is define the phi value. So phi is a tan 2 of y and x. And now let's just make a contour of that. Maybe we'll get rid of these other contours here. Contour of phi on z equals Lz. What is the angle at the other end? So this should just be telling us the angle. And yeah, it goes from 0 to 2 pi as we move around there. So this is the maximum one. There's the minimum one. That is the angle that things have moved by. All right. What next? Let's take this angle phi and then work out this calculation that we had here. So we've got phi. We can figure out what x prime is. X prime is going to be equal to x plus u. Y prime is equal to y plus v. And then theta is supposed to be equal to a tan 2 of y prime x prime minus phi. And I guess we should report that. Let's have a look at what theta is. So yeah, contour theta on z equals Lz painted. It looks like theta is very uniform at all different values. Theta is very close to this 2e minus 3. So that looks like it's the angle that we have, though things do get funky right around the origin where we have this division by 0 stuff going on in the arctan. Still, for most of the rest of the surface, we have a pretty uniform twist angle of 2e minus 3, 2.07 to 2.1. How does that compare with what we got in Maple? Pretty close. 2.07 to 2.1. That looks like it's right in the right range for what we had for this theta that we should have at the end of the thing. What about for the square cross section? In Maple, we found that that should have a twist angle of 2.465 using this different torsion constant than you would have had if it was just the second moment of area about that cross section. That would have been 2.667 or something. We calculated that in an earlier example. So now let's change this to a square going from, let's say, negative Lx, negative Ly, line to Lx, negative Ly, and then Lx, Ly, and then to negative Lx, Ly. Lx here is, remember, half of the side length. So this should be giving us the square that we're looking for and a twist that we're looking for as well. Aha, but something has gone a little bit strange here. You see, we've got mostly 0 for the angle, but we have some pockets where the angle is negative 2 pi, right? Just like it jumps up by that. So this is a problem that's showing up because of the way that we're calculating the angle and the periodicity of the tangent function. So here's how we can fix it. We can say that if we have something here where we get a number that's less than negative pi, we want to add 2 pi to it. So let's say theta test is equal to this thing, and we'll say that actual theta is equal to, if theta test is less than negative pi, then theta test plus 2 times pi, else if theta test is greater than positive pi, then it means that we went the other way, right? So we have something that's more than 2 pi in the other direction. Then let's subtract off 2 pi. then theta test minus 2 times pi. Else, if it's not less than negative pi or greater than pi, we'll just use the test one. So then it was working out perfectly. So this should be scaling things by 2 pi or pi, depending on whether we ended up with something that was more than negative pi in one direction or greater than positive pi in the other direction. Let's see. So it looks like it worked. We have a number which again is a little bit funky right around the middle, but most of the time it's this purple thing, which is about 2.3 of an angle shift, and that's pretty similar to what we got in Maple. So the plot tells you something. A lot of the time you want to just pick some spot and get the angle right at that spot. So let's just have a look at report val of theta at, let's say, Lx 0 Lz. And then we'll compare that to, what if we were to use the top right corner, Lx Ly Lz. So we have a similar theta at each of those corners going between 2.40 and 2.45 at the top right corner. Yeah, that's showing us some stuff that's pretty good there. The reason that these are a little bit different is perhaps because of warping. Let's have a look at the warping. So we'll take a contour of W on Z equals LZ. So do we have it fixed to no displacement there? Nope, we have it fixed to no load in Z on that surface. So if we look at the Z displacement on that surface, we assumed that was 0 when we came up with these analytical relationships, but is it? No. We can paint that to make that look a little bit more clear. So we do have some warping on that surface. It goes out by about 30 microns in some parts and in by 30 microns in other parts. This is not the case when we have a circular cross section. So if we go back to the earlier version where we had a circle, then the displacement is a lot lower than that. We now have, according to Flex, some warping, but it's like 100 times lower than the previous one. It's not E-5 anymore, it's E-7. So this is a pretty good approximation for circular cross sections, but for square cross sections, that's why we have to use things like different torsion constants and deal with more complicated things like warping. The next example has you explore some of the limitations of this FlexPDE solution by applying torsions the way we're applying it. If we take the Young's modulus and reduce it by a factor of 1,000, then you would expect that the angle will just go up by a factor of 1,000, right? That's certainly what will happen in the Maple calculation. We'll get 2.46 as the angle at the end. But this is quite a lot of rotation, and that is not what we're going to see in FlexPDE. We only have 1.22 as the angle at the end. So what's going on there? Why is the angle so much lower than what we calculated with Maple? The reason is to do with the direction that we're applying the stresses. So these stresses that we're applying in FlexPDE, as the thing rotates, it's not actually going to cause it to just continuously rotate and always be perpendicular to that original direction. This stops it after we've aligned with the new direction. So if you take a point down here and you apply a force in the y direction, after it rotates, Flex is still applying that force in the y direction. So even if you take the Young's modulus down by another factor of 1,000, we're going to limit in rotation to pi by 2 after we've rotated by pi by 2 and then just stop there, because now those stresses we're applying no longer cause a rotation, they just cause it to kind of pull apart at the top. So that is a limitation to the way that we're applying stresses here in FlexPDE. It means that these results will have another issue compared to normal. So not only did we have a lot of small angle approximation things going on in Maple when we worked this stuff out, and the limits between square and circular cross sections for this analytical work, but the way that we're applying stresses, the way we're applying loads on the top surface is going to always apply a force in a given, this is always in the x direction based on the original y value, and always in the y direction based on the original x value. So it's going to be limiting the amount of angle of twist that you could ever get from this to pi by 2, because once it's twisted that amount, Flex says the force is no longer in the direction that's causing it to twist more, so it just has moved by pi by 2, and that's it. So part of what made that example a lot easier to do in FlexPDE is the fact that we were started with a shear stress distribution, and that meant we had some work to do in Maple to figure out what moment that meant, but in FlexPDE we already had it in the stress distribution. What if we wanted to go the other way? What if we wanted to start with some moment and figure out the stress distribution that we would need? Well, similar to what we did in the bending moment section, we can work out that a stress distribution like this is going to work. So we've centered it around the centroids in Z and Y. If we're talking about on a ZY surface in the X direction now, then this distribution of stresses will produce a pure moment in X. So there's no net shear stress produced by this because we've centered the distributions on Z bar and Y bar. It doesn't produce any stress in the X direction because there's no axial component. So this is going to end up producing a pure moment when you work out what this integral is. And specifically, after you work that out and find out that the moment in X produced is this thing, which is just the same as our the square of the distance away from the centroid times this tau naught, you now can say, okay, well then to produce a given bending moment, not bending moment, twisting moment in the X direction, a moment perpendicular to this surface, you would just need that tau naught is equal to that moment you want divided by this integral. So that's why this shear stress distribution will produce a moment mx on any X surface. So this distribution has y-directed stresses that depend on the z distance from the centroid and has this negative sign in front because of how this works. So the more negative z you're in, the more you need the more y-directed stress will produce twisting moment. And we don't have that negative here for the z-directed stress because that z-directed stress, the one that points up, produces positive twisting moment in X depending on how positive the y value is compared to the centroid. So this is a stress distribution that will produce the moment, the twisting moment mx on an X surface. Let's test this formula using the previous example. So we found for a square cross section that we ended up with a moment of this produced by those these stress distributions here. So let's see what we would have calculated if we kind of adapt this for use on the Z on the Z surface. So on the Z surface, what was Y is going to be like X, and what was Z is going to be Y, right? If we kind of adapt this to a Z surface, we can kind of write out what that is. For a Z surface, we could then say that mz, that the stress distribution that produces a given mz is, put in another equation there, the stress distribution that produces a given mz is tau on z in the X, which is equal to something that depends on negative the Y value. So negative mz over this integral of RC squared over A dA. This now is over the area of that z surface times what? Times the y distance, y minus y bar, and tau on z in the y, given by positive mz over the rc squared dA over a z times the x distance away. So the more you are to the right in x from the centroid, the more torque you're going to be getting. So the shear stress distribution in y that you want to be applying to give a positive mz will be something which has more y stress the more to the right you are, just like here we were giving more z stress the more to the right you are in this picture. Okay, now this time we will say where RC is defined as the root of the distance that we are from the centroid. So in this case, it's going to be y minus y bar squared plus x minus x bar squared. Okay. Now for the mz that we have, we can check what we would get. So let's say tau zx check is going to be equal to negative mz times y minus y bar divided by the integral of rc squared. Okay, so let's work out those things. So we'll say integral of rc squared is going to be the integral over this cross-section of the square root of the distance from the centroid. So first let's figure out what the centroid location is. Y bar should be just 0, right? But let's put in how we would get that in general. Y bar is going to be the integral over the cross-sectional area, which is the same as this integral, right? Actually, let's figure out the area. So AZ is going to be the integral over the cross-section of just 1, right? And that should just be Lx times Ly. What did we forget? Semicolon there. Okay, so Lx, oh, not Lx, the Lx times 2, right? Because we're going from, oh, actually, wait a minute, hold on. I guess in Maple here, I made Lx1 and Ly1, made it the whole width of the thing and then divided by 2. Yeah, so Lx times Ly, either way, the area is 1. So then y bar, we didn't adjust this integral yet. Y bar is going to be the integral of y over this surface. And we should have 0. Indeed, it's just in the middle. It really would be this integral divided by the integral of 1 over that surface, but it is just 0, so it's not going to make a difference. Same thing for x bar. This is centered on the x-axis. It's a rectangular thing from Lx over 2 to in each dimension, so negative Lx over 2 to positive Lx over 2. So we're also going to find the average x position is equal to 0. Next, what will we get for this RC squared thing? We'll say that RC is defined as the distance from those average positions. So square root of y minus y bar squared plus x minus x bar squared. And that is just going to be root of x squared plus y squared. So we can say that the integral of that over the surface is going to be the same as these integral formulas, except we're not going to take an average. We're not dividing by the area. And what we're going to integrate is RC squared, right? That's what we wanted for this integral RC squared. Yeah, we wrote squared in the name. That's good. So next, how do we do for that? The average distance from the center of a square turns out to be a 1/6. Seems reasonable, I guess. The maximum distance would be a half and then another half. So it would be a half to the right and a half up. That's a half of root 2. So that would be 1 over root 2 is 0.707. And we've got 1 over 6 as the average, so it makes sense that it's less than that maximum distance for sure. And okay, yeah, so there's the average distance away from the center of the square. I guess that seems kind of reasonable. What next? Now that we've got this, we can say that tau zx should be mz times y minus y bar integral of rc squared divided by that integral thing. And what did we get? We got negative 0.1 E7 times y, which is negative 1 megapascal y. Exactly what we said the stress was in the x direction to get this moment. Where's that stress? There it is there, negative y times 1e6. What about tau z in the y? Check, according to this formula. It should be the same thing, but with a positive and x minus x bar. And indeed, 1 megapascal times x, which is exactly what we said tau zy was at the start of this. So this means this formula is able to reproduce the setup that we had for the applied shear stresses to get this thing to work. Can we try it for the circle section? This one's a little more complicated because the area is a little more complicated, but it should also work for this. So how are we going to do it? We're going to say that y bar and x bar, again, we know that those are just going to be 0. So let's just save some time and not bother to calculate that. We'll have RC is equal to square root of y squared plus x squared, because the y bars are 0. And then int RC squared will be equal to the integral, the same integral, except what we're integrating is now RC squared. Yeah? So what do we get for this? What do you think it's going to be? It should be less than this 1/6 because the circle has less far distance away than the square does. So we got pi over 32. How much is that? Pi over 32. It is 0.98. It's less than a 10th even. So a fair bit less than a 1/6. Yeah, actually these look familiar, don't they? This is telling you this one was the size of the torsion constant that we had here, and this one was the size of not the torsion constant we had here, but the moment that we were applying in Z on this part. Okay, yeah, so this one is, actually in the first case, it was not just the torsion constant, but also that moment. So this seems like it's going to be leading us towards the right answer in this stress distribution as well. So again, we'll say that tau Zx check is equal to negative mz divided by this integral times y minus y bar, and we'll say tau zy check is positive that thing times x minus x bar. Let's see. So, yep, so look, notice the pi there divided by pi is going to give us 1 megapascal with a negative in front of the y, and then positive 1 megapascal x. So there we go. It works. Way back at the beginning of this section of notes, we pointed out that for axial stress and strain, we have a meaningful macroscopic relation on Hooke's law. So we'd say that a spring has a total force that it's producing given by K times the length change of the spring, and this is related to the microscopic by saying what that spring constant is. So by substituting in that the force is stress times the area and the change in length is the original length times the strain, you can say that yes, this does agree with what we've got in our microscopic Hooke's law, as long as the spring constant turns out to be AE over L. The same thing actually is true for torsion. We can also write a macroscopic kind of twisting spring constant rather than like stretching spring constant, and say that the torque applied is equal to the spring constant for twisting times the twist angle that we have at this spot we're applying the torque. So the twisting torque divided by twisting angle, after substituting in the other stuff over here, you can see that the torsional spring constant has to be the shear modulus times the torsion constant divided by the length of this rod. And this is what's going to allow us to, again, solve kind of macroscopic problems with moments applied at specific spots and sort out how angles of twist are going to vary across complicated systems like this where you have things matching with gears. In this problem, we have two steel shafts, AC and FD, and they're coupled together with this meshed gear system. So the gears are like meshed together. When this one rotates, this one's going to rotate in the other direction, and they're going to translate the force the same at this meshing point, and that means that the torque that is applied at gear C is going to be, or on gear C from this force, is going to be less than the torque that is applied on gear D from this force. So this is a way that you can step up the torque that's applied across this junction. So the torque that we're applying here, we've got a point moment of 12 Newton meters applied here and 4 Newton meters applied here. We end up stepping up the torque as we jump across this. So if this is 12 Newton meters, then the gear D must apply to this shaft. If it's 3 times the radius, we expect that it's going to be applying 36 Newton meters in the opposite direction, because when this one twists this way, the other one is going to twist the other way. So we're going to drop that by 4 and end up with 32 Newton meters of torque in this part. Peak torsional moment, moment, is going to be in this little segment between E and D, and that's going to be where we have the full 36 applied there. So you see, this is kind of building up the moment by jumping up to there, but how do you get that? How do you get energy for nothing? Well, you lose on the displacement. So the twist angle that this one has is going to be a lot more than the twist angle that shows up here, right? So for this gear to be applying the same force to this gear as this gear is applying to this gear, we end up with a couple of different things happening. We have this as a smaller radius, meaning that we have less torque applied to C compared to the torque that gets applied at D. But that also means that the angle that C rotates through is larger than the angle that D rotates through. So the work done, which is kind of like torque times the angle, just like work is force times distance, is going to be the same. So that's how energy ends up being conserved from one gear to the other. So that's the analysis that we can do by thinking it through at the start. How do we get that intuition to be able to do that, though? First, let's get a little bit more systematic and break this up and talk about it a bit. So suppose that we're just going to call the twist angle that D goes through in this direction using the right-hand rule, so that'd be the same direction that this moment is showing, theta D, and we're going to show this twist angle that C goes through along this thing as theta C. We'll figure out how to relate those in a minute. Actually, they need to be related negatively, right? Because if this one rotates this way, the other one has to rotate the other way. Now, what about the torques? We can say that the internal moment at each point would be determinable by this diagram. So we've got a pure applied moment in this direction by the right-hand rule here. That's 12 Newton meters. We've got nothing applied at A. So that means if this segment's going to be in equilibrium, there can't be an internal moment between A prime and A. We need to have no, so we have no displacement over here at point F, and we're going to have a reaction moment applied by the wall because it's a fixed support. So A is a pin, can't apply a reaction moment, but F is a fixed support, so it can. We'll draw its reaction here as TF, like a reaction torque. Yeah, it's a pure moment that it's going to apply, but, it applies a torque as well by it being a moment. A moment is just a special case of an applied torque. Right. So the internal moment at each point, we could call it, with this sign convention, say that the twisting moment is the one that's aligned the same direction as we would draw a normal force. And now with this setup, we can start to form relationships between the angles and the internal moments and also the torques at this junction. So we've got a couple of different things. We've got the Hooke's law for torsion, which lets us relate the slope in the angle per step in Z to the internal moment and the torsion constant and shear modulus. We can figure out what the torsion constant is by knowing that it's a 30 millimeter diameter, and we are given the shear modulus for this rod. The twist angle at any radius within a gear is the same. So the twist angle at any radius in here is the same, and the displacement of gear teeth is the same for each gear. Like the amount that this tooth displaces is the amount that this tooth displaces, and that means that the arc length at this junction has to be related like this. So theta d, the amount that this one rotates that way, times RD has to be equal to negative theta c, because theta c was the amount by the right-hand rule that this one rotates this way. So negative theta c is the amount that it rotates this way, times RD. So that gives us a relationship between those angles because we know the gear radii. Similarly, for the force vectors, these force vectors are Newton's third law action-reaction pairs. So the vectors themselves are equal and opposite, but the components that we've drawn, the magnitudes, this way and this way, have to therefore be the same because we've drawn them in opposite directions already. So the components of CD in the up direction has to equal the component of DC, force of D on C, in the down direction. And now the torque that is produced on gear D in this direction would be R cross F, right-hand rule, it's in this same direction. And the torque that's produced on C, torque DC, would be R cross F, also in that direction by the right-hand rule. So if this force equals this force, and the torque is equal to RC times FDC, then you can say that FDC is equal to that torque divided by RC. And similarly, if TCD is equal to RD times that force, then that force is equal to that torque divided by that radius. So this tells you how the torques are related. Just as a sense check, we've got that the angles are negatively related because when one of them spins this way, the other one spins the opposite direction, and that D is going to spin by less than C spins because D is at a bigger radius. But similarly, the torque on D is going to be larger than the torque on C, again because D is at a bigger radius. So you notice here the radii shows up in the denominator, here it shows up in the numerator, and that's how energy gets conserved. Just to reiterate, the forces at the intersection are Newton's third law action-reaction pairs, but the torques produced on each gear by the other one are not Newton's third law action-reaction pairs. So they end up pointing in the same direction and having different magnitude due to the gear ratio. So let's go ahead and solve this then. We've got a couple of things that we can put in. We can say that the torque here, let's do the internal moment on this part. The moment Z in here has to be 12 Newton meters, and that means that this torque, TDC, is equal to negative 12. Then that means TCD is equal to RD over RC times TDC. And that's going to solve for what that one is once we put in the gear radii. RD is 0.12 meters, RC is 0.04 meters. So now we've got 36 Newton meters applied at the end of gear D here. TCD is negative 36, so it's actually pushing in the other direction. Why is that? We twist this there. That one twists like this, so we've got this thing being twisted like that, which is in the opposite direction of the angle that's shown here. Okay, now we are going to, we can write out what the moment is internally after we go and solve for TF here. So let's see. The net torque on this thing is equal to 0 in the length direction, in the like Z, I don't know which one is Z, but the longitudinal direction. So we've got negative 36, so 36 to the left here. We've got 4 Newton meters to the right, and so this one has to be the balance of those things. So TF has to equal 4 plus TCD, but TCD ended up being negative, so it ends up being negative 32. Now we're in a position that we can write the internal bending moment at each point. So we could say mz for FED is equal to, let's see, TF plus piecewise negative 4 as long as Z is greater than, what's that, 1.5. 1.5, and then we're going to add another piecewise of negative TCD if Z is greater than 2 meters. So that'll be MZ FED. Where did we mess this up? Oh, I did it backwards. So first you give the Z range, and then the value, and then over here that'll mean we go Z is greater than 2, and then we'll give that value. So let's plot this. Plot MZ FED, Z is 0 to 2, and what do we get? We have some large, well actually this is, let's say T equals negative 36 to 36. So it's some negative value, and again the peak torque is between point G and point D. We could also come up with the internal bending moment in this range, and that one will be MZ CBA, which is, we've got this applied to the right, so we would say negative TDC plus piecewise, whoops, I've opened PowerPoint again. Strange hotkey. Piecewise, Z is greater than 1.25. That's this distance over there. Negative 12. And then we should have it going back down to 0 after that. So let's make a plot of not just MZ Fed, but MZ CBA. And we've got it at 12, and then dropping down to 0 after we pass that point 1.25. The largest shearing stress will be something we can determine from the largest internal moment. So you might remember that we worked this out earlier, how the shear stress is related to the torsional strain. This was all the way back in section 9.1, where we figured out that the magnitude of the shear stress is equal to G R del theta by del Z, or just the radius times the moment divided by the torsion constant. So we can say that tau max value is equal to R times mz over jt. Now we're going to need to figure out what these components are. So we have mz, we'll just use the maximum mz that we got here. So we'll say mz max FED is equal to subs z is equal to, let's say 1.6 into mz FED, and mz max CBA is substituting z is equal to, let's say 0.4 into mz CBA. So those are where each of these internal moments are a maximum. And then we'll say that the maximum stress comes from the torsion constant on this circular beam with an R is equal to 0.03 meters, so 30 millimeters, and that's also going to make the tau max at the external radius. And we'll need to figure out what the torsion constant is for those things. So we have torsion constants in this section here in the 9.1 section. For a circular cross section, it's just pi by 2 times r to the 4. And JT then will be 3.14159 over 2 times r to the power of 4. I'm using this approximate pi so that it forces it to be a decimal number. Yeah. So now we just need to put in the maximum mz for each of those different segments. Maybe we'll say tau max FED is equal to subs mz equals mz max FED into tau max, and the same thing for CBA. And where do you expect the shear stress to be larger? Well, certainly in larger magnitude in FED, because FED has a larger maximum internal moment, and they are the same shaft. So they have the same outer radius, same torsion constant. So when we work this out, we'll find that there is much more shear stress in FED. So if the beam is going to break somewhere, it's going to break where the shear stress is a lot larger, and that is going to be in the first segment in FED rather than in CBA, where the shear stress is lower. To find the twist angle, we can make use of the fact that the slope of twist angle per step in Z is mz over JTG. We can put in what G is. G is equal to 80E9, and then theta for FED would be equal to, starting at 0, we're going to integrate this thing on FED. So integrate mz in FED over JT times G from Z is equal to 0 to Z. So this should be the twist angle at any point in FED. And yeah, it depends on how large of a Z you put into this, what we're actually going to get. But what we can do next is we can say theta CBA is equal to, first of all, the Z we would have gotten at the end of this is Z is equal to 2. So we can say that we're going to start with theta FED subs Z is equal to 2 into theta FED, and that'll be the starting twist angle. Oh, actually, this is a little bit more complicated. Let's work this out. This is theta D, right? So theta D is equal to this thing. Let's suppress this output. And we've got this value. Can we simplify it? It doesn't know whether 2 is less than 1.5. Are you serious? Let's just try evalf and see what that's giving me. All right, so we've got a twist angle which is equal to this, and we can also just plot that twist angle along FED. So plot theta FED from Z is 0 to 2. Just have a look at that. What's the twist angle do? You expect it to be pretty linear because the internal moment is almost the same all along this length. Yep. There we go. So there's the twist angle at theta D. Theta D has a negative twist angle because we reasoned that the twisting moment is actually in the opposite direction here. But that makes this one go in a positive direction because of this relationship that we worked out. So theta C is negative RD over RC times theta D. And that should be quite a bit larger than the angle we have here for theta D. Theta C is negative RD over RC times theta D. So we've ended up with negative 3 times this as our twist angle in at gear C. But we're not done yet because we're still applying this moment. It's going to make it twist even more along this length. The moment is not as large, so it's not going to be adding as much extra twist angle as we move as it was over here, but we're still going to get some extra twist angle. So we can say, similar to how we set up theta fed, theta CBA is going to be the integral of mz CBA along the length Z, except that we're going to start not at 0, but at theta c. And now we could plot that one as well. Plot not just theta fed, but theta, oops, forgetting how to type here, theta fed plus theta CBA. And what do we have? Oh, that's weird. Why did we only get one of those? Ah, we added them. I meant to say theta fed and theta CBA. Plot those two things together. Yes. So we have theta CBA starting at a much larger angle and then increasing up. It doesn't actually exist for this last little bit because it's only 1.5 long and not too long, but that's okay. We haven't, we don't have any change in the angle there anyway. So now we can figure out what the angle of twist is at A. Theta A finally is subs Z is equal to 1.5 into theta CBA. And now we figured out everything. We figured out the angle of twist. Well, if we ask Maple to figure out whether 1.5 is smaller or larger than 1.25, yeah, so we've got the final angle of twist, and notice that it's a little bit bigger than theta C, not a lot bigger, because we don't have much moment along this shaft compared to the first one. So a lot of the actual twisting deformation happens along this first shaft and then gets magnified by a factor of 3 from the gear ratio, and we get a twisting of this as well. If these were all perfectly rigid, then because this is fixed over here, this would not produce any twisting at this point. But because it's not perfectly rigid, it's very stiff steel, but we're still applying some twisting thing here. We are going to get some twisting deformation. Not a lot, but some. Whoops, just realized in checking over the solution I did for this earlier that the numbers are different and traced it back to using a different radius. So this was actually the diameter of the shaft. It gave us the radius of each of those gears and the diameter of the shaft. So I fail in English reading comprehension this week and should have put in R is 0.03 over 2. Now conveniently we're using Maple, so while if we had done all this on paper, this would be just a disaster. By using Maple, we can just hit enter and it will calculate everything out again and give us the new final twist angle. So how did that change things? This is kind of interesting. It should change it a lot, right? Because it goes like r to the power of 4. So previously, when we had, if we made the shaft twice the diameter, we found that the final twist angle was 0.002 in radians. Now, when we make it half the diameter, the twist angle goes from 0.002 to 0.03. So it jumps up by a factor of about what? 11 and a half, 12? Yeah. So not just a factor of 0.002, but goes up by a factor of 10. Oh, sorry, not 12, like 15. It goes up by a factor of 15. It's 10 and then multiplied by another 50% on top of that to go up to 0.03. Yeah, so making the shaft a lot thinner has made things twist a lot more. In fact, it should go up by exactly 16 since this scales like r to the power of 4. So when we put in this factor of a half in there, we are going to be having everything increase by 2 to the power of 4, which is 16. So now we've figured out how to deal with axial stress and strain and shear stress and strain, and also with bending moments leading to bending deformations and even torsion leading to twisting deformations. And I know what you're thinking. Well, that's all well and good for these isolated problems where you have just one kind of these, but you know what? Can't we deal with a problem where we have all of them at once? Yes, we can. And that's exactly what we're going to do in combinational elasticity. So for arbitrary loading, a beam is going to experience axial, shear, flexure, and torsion strain simultaneously. If strains stay small enough for Hooke's law to still be valid, then the linearity of Hooke's law means that you can use superposition. That is, to find the total deformation from arbitrary loading, add the displacements calculated from the axial shear, flexure, and torsion strains together, superimpose them. So let's give this a shot. We've got a cube with a stiffness of this. It's a cube. Side length is 1. This is the Poisson's ratio. And we're going to say that it extends from 0, 0, 0 to LLL and is fixed on its x equals 0 surface and subjected to a force and moment at the end evenly distributed over the x equals Lx surface. So that's the end, the x equals Lx surface. And we're asked to find the reaction force and moment produced at the support. So that's the fixed support at the x equals 0 surface, and find the displacement of the LLL corner of the cube. The first part of this is something that we could do in week 3. The second part is something we can only do now after we've had 6 more weeks to explore how this stuff works and incorporate all this elasticity stuff. So here's how we're going to do this. Assume that there's some kind of reaction force and moment applied at the left, like we did in week 3, and we're going to say that we can use Newton's second law in statics all in 3D on this thing, just like we did in week 3, where we say the net force is equal to 0. So whatever force we're applying here has to be the same as the force, has to add to this force that's applied at the end to give us a 0 vector. And the torque about any point that we like has to be 0 as well. So we could say that the torque at point 0 has to be giving us a net, has to be 0, right? So what would the torque be? We'll take 0 cross the reaction force if we assume that it's applied at this point and calculate the reaction moment accordingly. And then we'll have a displacement of L00 to point, the point where F end is applied. And the reaction moment adds directly without having any cross product, and the moment at the end adds directly. So this gives us 2 equations that we can solve for the 2 vector equations that we can solve for the 2 vector unknowns, the reactions. So we'll remember how this went in week 3. Again, that was a long time ago, with linear algebra. And we'll say that we've got F at the end, which is given by this, 200, 300, 400. And we've got a moment at the end. We call this F end. Yeah, M end is 300, negative 200, 500. And then what are we going to do? We're going to say that we have the net force on it is equal to 0, which tells us what RF has to be. RF, the reaction force, has to be equal to negative F end by solving this first equation, and the reaction moment has to be negative the sum of these different things. So the reaction moment, we can put in what L is. L is 1, and then Rm is equal to 0 cross RF, that's just going to be 0, plus L00 crossed with F end, plus M end. And we're going to have negative all of that stuff added together. So there we go. There's our reaction force and reaction moment. Now that we've got that, you can imagine making a slice through the beam and looking at any cross-section and say there has to be an internal force and moment that would counteract what's being applied there. So right away, the internal force, F internal, with no distributed load along the length, has to be equal to negative the reaction force, and the internal moment we could get by doing by using the torque equation, right? So we have to have the net torque produced on this thing about any point is equal to 0. So let's say about the left point is equal to 0. About the left point where we applied the reaction force, we don't have any torque applied by it, but we do have a torque applied by the internal force. So just like calculating this thing, we're going to say that the internal moment is equal to negative x00 cross F internal plus the reaction moment here being added to this thing. Okay. So this comes from saying that the net torque on this about the left-hand end would be x00 cross the internal force plus the internal moment plus the reaction moment. So you solve this for the internal moment and you'll have negative those other things. All right. So the internal force is a constant, but the internal moment that we're applying depends on x in its second and third components. The reason we wanted this is because these internal forces and moments determine what the displacements will be via the Hooke's laws. So we can take this internal set of forces and convert it into internal axial, normal, and shear stresses along this beam, and the internal moments, and interpret them as bending and torsional moments, bending and twisting moments, and then determine what all of the displacements that would be caused by all of those things acting together is. Specifically, the internal force we found is going to be equal to the internal stresses multiplied by the cross-sectional area. So the first component is the force on the x face in the x direction, and that means after you divide out the area, you've got the x-directed stress. And that x-directed stress is going to be leading to an x-directed strain via the axial strain stuff. So the strain is equal to the stress over the Young's modulus, and this is going to be telling us how much we've got as our displacement in x. Now, the other components on the x face in the y direction and on the x face in the z direction are going to be the shear stresses on that face multiplied by the area, and those will lead to displacements through shear strain according to these equations. According to the shear stress divided by the shear modulus, that'll tell you the shear strain. Now, the shear strain, how do we turn that into displacements? If we assume that the surface has no x displacement shear strain, which is reasonable because the back side is fixed, so shear will be causing just this sliding vertically if we've got on the x and the y, rather than rotating in the x direction, rather than like the sliding along the x direction, then it's okay for you to say that this shear strain, which is really the sum of those two things, del v by del x plus del u by del y, is entirely manifested with del v by del x. So the shear strain will be just this del v by del x, and that means we can say that del v shear by del x is equal to tau xy over g. Now, why did we call this v shear? Because we've got other sources of y displacement. Another place we can get y displacement is via the Poisson's ratio. So this x stress doesn't just lead to displacement in x. Really, we should say that the normal strain that shows up is, due to some normal stress, is coupled to it by the compliance matrix, and that gives us, if the other stresses are zero, so if it's free in y and z on these cross sections, then we can use that to figure out that we have an axial source, a normal stress source of displacement in y and z that are modeled through the Poisson's ratio and the x stress. Next, we have the moments. So the x component of the moment is causing a torsion, right? That's the axial directed moment for this beam that's extended in x from its support, and that is leading to a twisting around the x-axis via the torsion stuff we've been doing this week. But the other two components are bending moments. So the moment in the y direction divided by flexural rigidity in y is telling you the rate of z displacement per step in x, the second derivative of that, the curvature in z. Why is it negative? Because a moment in the y direction using the right-hand rule would make this beam bend kind of into the page, and that's a negative z displacement there. The moment in z, though, is the one that we were dealing with most of the time last week. This moment in the z direction would be out of the page, and that's going to be causing a curvature in the positive y direction through the flexural rigidity in that direction. So we have a number of different sources of y and z displacement on this cross section. The x displacement is really very straightforward compared to the other ones, but the y and z displacement, even if angles stay small, is a source, can be caused by shear, axial stress, flexure, and torsion, because this twisting angle, depending on how far away we are from the centroid, is going to be leading to different displacements in y and z. This one is using that small angle approximation stuff we did at the beginning, which was, where was that? I think it was here, this section where we worked out the polar coordinate transformation. So the displacement in the right direction is based on negative the up amount times theta, and the displacement in the up direction is based on the right amount times theta. So here we are saying that the displacement in the y direction, which is to the right, is based on how much we've displaced in z times theta, and the displacement in the z direction is based on how far we are up in y times theta. Let's just check that. How far up we are in y times theta in the x direction is going to make us bend towards z, and that's why we have a positive number there. But the other one, how much into the page we are in z, times a theta in the x direction, is going to make us bend towards y. And that's where the negative is from, because it was into the page rather than out of the page, causing that displacement. Okay, let's work this thing out. So we'll say, we'll just put in some line breaks here. That has us able to see everything that we're working out. Depends on the specific point on the surface AX we're talking about. We'll put that down there. Put that down there. Okay, so now we can see all of the analytical work that we did and start working this out in Maple. In this case, the cross-sectional area is just equal to 1. So we can now figure out what those stresses are by taking sigma x is equal to F in's first component over AX, which is just dividing by 1. And then we can use that sigma x divided by E. Let's put in the material parameters as well. We said in this example that it was 70 gigapascals, and nu is 0.3. So that, oh, and also we have a square cross section. So later on we're going to need what? We're going to need what JT is. JT for twisting of a square cross section with a length of L is pi, no, not pi, it's 2.25 times L over 2 to the power of 4. That was our JT at the start of this for a square cross section. And what else do we have? We've got the flexural rigidity. We're going to need to figure out what the flexural rigidity is for rotation of this cross section in y and z. And conveniently, the b and the h are the same. So EI for each direction is going to be equal to E times L to the 4 over 12. So that's all well and good. And what is next? We have to work out G, shear modulus. So G is E over 2 times 1 plus nu for an isotropic material. Next, so that's the stress. And now we can say that we're going to be having a del U by del X, which is sigma over E. So that means that U at the end is equal to just the integral of Sx over E from x is 0 to L. So this should be the displacement of the tip in the x direction. Great. The other ones are a fair bit more complicated. Let's work out what the y displacement is altogether. So we'll say V shear will be equal to tau xy, which is the second component divided by a. So let's just call that S on x in the y is equal to F internal 2 over AX. And we'll take that stress. And if we divide it by G, then we're going to have the slope of the shear displacement. So we'll say V shear would be equal to the integral of Sxy divided by G from x is 0 to L. And what else are we going to have? So shear displacement of the tip is more than the axial displacement of the tip in this case. What else? We've got normal displacement because of V axial del V axial by del Y. This is a little bit complicated what to use for this. We really should use the sigma at the end and then kind of integrate from the center line out towards the edge. So let's go with V axial would be equal to the integral of negative nu times sigma x at the end, but sigma x fortunately is independent of x, but let's say subs x equals L into sigma x. Yeah. Let's just work, maybe we'll work this out separately so we can deal with the integral. What is this thing? This would be the strain, right? The strain at the end of the beam. So we'll call this epsilon in the y direction at the tip. And this is going to be equal to negative nu times Sx over E, the sigma x divided by E, evaluated at x equals L. And now if we take this epsilon y at the tip and we integrate it from y is 0 to L over 2, we'll have the axial strain, which is due to this Poisson's ratio coupling. And it's going to be quite small because the axial the axial strain, even in the x direction, led to not very much displacement. And now we've got a smaller amount through Poisson's ratio and a smaller distance from the center to the edge. So this really doesn't give that much displacement in this problem. All right, let's keep focusing on the y displacement, and then we'll loop back and do all the z displacements. So we also can have a y displacement from the z moment and the flexural rigidity. And the z moment depends on position. So we've got mz is equal to m internal's third component. And the curvature, then depending on position along the beam, we really will need to, if this is the curvature in the y direction is equal to mz over EI. EI fortunately doesn't depend on y or x this time because it's a square cross-section and constant E. So with that being the curvature, we can take the slope from flexure and find, in fact, the flexure displacement by integrating twice, and we expect to add no constant to this because we have no slope and no displacement at the left end. So in this case, we're able to just do two integrals and say V flexure at the tip will be equal to the integral of cy from y is 0. Actually, hold on, one step at a time. V flexure is the integral of this y is 0 to y, and then y is 0 to y. And then we're going to substitute in y is y tip to figure out what this is at the end. Oh, wait a minute, this is the wrong thing. We're integrating this with respect to x, so along the beam length, which is x there. Yeah. So then V flex tip will be subs x equals L into V flex. And bending is usually pretty prominent, but this is a cube, so it's going to be around the same size as the shear displacement probably. Yeah, it actually ends up being quite a lot more, about 6 times as much. Why would that be? Did the bending moment that we're using happen to be a lot larger? So negative 300 times x, x goes 0 to 1 plus 800. So it's mostly 800. It goes down to 500 by the time we're at the end. And the shear was only 300. Okay, so the bending was just a lot more prominent in this direction to cause a lot more of the displacement in this problem. And the last thing is the torsional displacement. So we can figure that out by taking mx as the first component, and we worked out jt and g, and we'll say that theta is equal to the integral of mx over jt times g from x is 0 to x, and then work out what theta tip is by just substituting x equals L into that. And then, once we've got that twist angle at the end, hopefully pretty small, yep, quite the small twist angle, we can find out what the vertical displacement is by looking at the peak negative z. Oh, wait a minute. We are looking for the point which is at, so we have one corner at 0, 0, 0, and we have another corner at LLL, and that's the one we're finding the displacement at. So at that point, we are at a displacement in positive z of L over 2. And this twist angle at the front corner will make it bend in the down direction. So we've got the torsion at LLL, let's call that, that's like the tip corner there, is going to be equal to theta tip times L minus the L over 2, but it's negative, really the negative Z position that we're at there. So this is going to cause it to bend down. Yeah. So the flexure, because we have that positive moment, is trying to make it bend up by this amount. The torsion, the twisting of this thing, is making it bend down by that amount. So we should be able to find out V LLL total by taking V shear. We just called that V shear. It's really V shear at the tip, plus V axial at the tip, plus V flex at the tip, plus V torsion LLL. We weren't really consistent with the naming convention, but this should be telling us the total displacement in Y at that tip. Now we can go in and figure out what the displacements in Z are using the same stuff. So same idea. See if you can use that logic to figure out the Z displacements. So W, well, first we'll figure out tau x in the Z, which is equal to the internal force's third component, and then we'll get, that divided by the area of x, but the area of x is just 1, and we can say that the shear displacement, W shear at the tip, would be equal to the integral of tau x in Z divided by g from x is equal to 0 to L. So this thing is just a constant. We don't get any funky stuff going on there. Next up, we've got W axial at the tip, which is going to be, let's see. So we have this thing. Let's again figure out epsilon in Z at the tip, and that'll be negative nu times sigma x at the tip divided by E, but sigma x is just a constant all the way along, so we've already got that evaluated at the tip. We don't really need to say sub x equals L into Sx, but let's just go for it. And now that we've got that, we can figure out what W axial will be at the corner by saying W axial LLL is equal to the integral of EPZ tip from x equals, from really Z equals the middle to the end. Yeah, I think, did we do that before? We said axial y is 0 to L over 2. It's going to be exactly the same. The displacement from 0 to L over 2 is going to be the same as from the center to the edge. So that should be our axial one. And we can now go and figure out the bending one. Where do we get bending from? We get bending in the z direction from the moment in y. So C in z, curvature in z, is going to be my, which is m internal 2 divided by ei. And then we can convert that to a displacement by saying w flexure is equal to the integral of cz. Actually, I missed a negative sign there. This is the curvature in negative z. So integral of cz from x is equal to 0 to x, and then x is 0 to x again. And then we'll say w flexure tip is equal to subs x equals L into w flexure. And yeah, so again, the flexure is pretty prominent, but we had different moments in Z than we had in Y. So it's not as strong as it was in Y. What about the torsion? The torsion should be the same size, but from this twisting moment, we're actually going to be moving in positive Z at the tip. So the torsion, we already worked out what theta was, and now we can say WLLL total, because it's a square, WLLL tip, W torsion, LLL, that's what we want to call that, is equal to positive theta tip times L minus L over 2. And then we'll say W torsion total is equal to W shear tip, the one from just the shear stress on that X face, plus W axial LLL, the one from the Poisson's ratio coupling of the normal stress on that face, plus the flexure displacement, the one from the bending moment in the y direction, and then finally plus the torsion, the one from the twisting moment in the x direction causing that face to rotate. And altogether, it looks like if we, where did we not do things correctly? Maybe the flexure? Oh, did we say flexure? Yeah, we meant flex tip. There we go. Altogether, more displacement in the z direction than we had in the y direction, mostly from the fact that the torsion and flexure were working in the same direction on this surface compared to what was going on in the y direction. Now let's see if we can build this up in FlexPDE. So we'll save this as a new example problem. What's this problem? 9.3. And we have to change up the material parameters. So we're going to go back to the start and make sure we didn't type those in incorrectly. We've got an E of 70 E9, a Poisson's ratio of 0.3 again. And what else? We've got a rectangular prism, and everything is 1. Now let's go down and make sure we're actually drawing that. Nope, we want to go back to this rectangular prism thing that we had, except that we need to change this to do the regular old 0, 0, LX 0, LX LY, and then 0 LY to be drawing this square thing. Okay, now that's not the right stress. We need to put a stress on the far X face in this thing. So we're going to free the bottom and the top surface, but we are going to put a stress on the far X face. And the far X face is the one between LX0 and LXLY. So we'll stop here and we'll put in a new boundary condition. boundary condition on this surface is going to be load boundary conditions on U, V, and W, which will make up the force and moment all applied on that surface. So we're going to have to do some work to figure out what that is. Then, just before we forget, after that, we are going to be putting in that the load goes back to 0. And then on the back surface, from 0 Ly to close, which is this one, we need to fix it. So we'll say value of U is 0, value V is 0, and value W is equal to 0. Let's just write out what is going to be happening on the load on this surface. So load in the U direction on the x equals Lx surface is going to be Sx, the x-directed stress. The load in the V direction would be the xy shear stress. And the load in the W direction would be the xz shear stress. Now these are the names of the arbitrary shear stress that we're using inside our program, so we can't actually use these names. But let's just say that the stress there is Sx tip and Sxy tip and Sxz tip. Then we need to define what those things are up here in the definition section. So we'll say Sx tip equals, figure out what that is, Sxy tip, figure out what that is, and Sxz tip, and figure out what that is. The easiest one of these to figure out is the stress in X. So because the stress in, well, at least part of the stress in X, we can figure out the offset stress in X, not the one that's producing these two bending moments, but at least the overall average one, which is responsible for the net force on the end. This would be 200 newtons over the area of X, right? Which is just 1 meter squared. So if we put these to 0, then this should already be producing the X displacement at the tip. So let's report that. Let's report value of U at Lx, Ly, Lz, and just see what we have there. What do we not know about? Line to close. So here's our deformation now. If we put in just the X stress and we calculate that the X displacement at the tip is 2.8 nanometers, whereas in Maple, we also found 2.8 nanometers, 2.86, instead of slightly less here, slightly less likely due to the anchor stopping it from being able to move totally and pulling it back a little bit more than we calculated there. So far, so good. We are also in a position now to see what the V and W displacements would be just from the Poisson's ratio. So let's have it also report what V and W are at that tip. And we get negative 4.4 E minus 10 in each direction. Is that what we calculated here? Where are we here? V axial. Yeah, 0.4 something E minus 9. So 4 point something E minus 10. So about the same size as we calculated in Flex, but the one in Flex is slightly larger because we end up with more stress in those directions again because of that anchor. That's increasing the stress in Y and Z compared to what we would have had in increasing the strain that we get in those axial directions. The next easiest stresses to build in are the shear stresses that produce these net forces. Again, because the area is just 1, those ones we can find out by putting the stress in the Y as what we would want in the Y direction, 300, and the stress in the Z as what we would want in the Z direction, 400. And now we should be adding in and being pretty much dominated by those shear stresses except that these shear stresses will also be responsible for putting moments in this. So we should have not quite the displacement we would have predicted from just shear alone, but it'll be closer. It might be closer than what we would get when we incorporate all the bending moments as well. So we've got 3 e minus 8 in the y direction. Has the x1 changed? Not really. What about the y1? 3 e minus 8. This is not nearly as large as we predicted. Oh, wait, it's larger. This is 1 e minus 8. We got triple that because it's not in pure shear, right? So we, as before, when we allow it to bend from that shear force that we're putting on the end, we get more displacement than we would have otherwise. Okay, and same thing in W, no doubt. Yeah, W shear tip is not nearly as large as this W displacement we're getting. That's because even though we only applied the stress at the end that would produce this thing and not the pure not the pure moment that we're applying at the end, we are getting the same we're getting the effect of bending as well, and it's more than just what we would have predicted by using those shear displacement formulas alone. But there is a way to check this, and that is to go back to the very start of the problem and to say that m end, instead of this thing, is equal to 0. And now we should be doing in FlexPDE exactly what we are doing in Maple, and we can see how close these things are. So V total we calculate in Flex as about 3e minus 8, and in Maple we found about 3e minus 8. And for the W, we said about 4e minus 8, and we have about 4e minus 8. Not so bad. So this seems like it's working, at least when we don't have any of this moment applied at the end. To apply this bending moment at the end in FlexPDE, we need to figure out what stress to add that is going to add no net force, but just a pure moment. And fortunately, we've already worked this out in the bending section for how to get a given bending moment in Z or Y on this X surface. And in this section, for how to get a given twisting moment on an X surface. So let's incorporate these. According to those formulas, we need just to know what m end is. So let's make a new thing here. Restart. M end is that. And then we can say y bar is, so let's say L is equal to 1, y bar is equal to L over 2, Z bar is equal to L over 2. Those are the midpoints because we start at 0, 0, 0 and go to LLL. So these are the midpoints of that surface in X and Y. What do we need? We're going to need MZ is equal to M and 3. MX is equal to M and 1. And MY is equal to M and 2. Did that in sort of a strange order. That's all right, though. RC in this thing here was equal to the square root of the average of the, so this is the distance from the centroid. So this is the square root of y minus y bar squared plus z minus z bar squared. And we can now put in, I think that should be it, right? Now we can say Sx prime, the stress distribution to add, would be equal to negative mz times y minus y bar over the integral of y minus y bar squared from over the cross section. So what are we gonna, how do we do this integral? We're gonna integrate that thing from y is 0 to L and z is 0 to L. Similarly, to get the little bit of, okay, wait, this is Sx prime to put in for mz. This is Sx prime for my. We're going to have positive the my that we want times z minus z bar. Let's just check. If we're at a positive y position over to the right, then we want to be having, and if we have more stress over there, that's going to be creating something that is going, where's our coordinate axes here? I guess we don't have a picture of it here. But z is on this surface. Do we have an old one? No. Okay, we'll make a new one. So on this surface, the X out of the page surface, we've got y to the right. Whoops, wrong font. Y to the right and z going up. So according to this formula, we're going to get a moment in the z direction based on how far we are to the right and the stress out of the stress into the page, the negative sigma z. Yeah, that seems right. So if we have stress into the page here at some distance to the right, that's going to be creating a moment in the positive z direction. But to get a moment in the y direction, we need to be at an out of the page stress when we're displaced up. So that's why we have my without that negative times z minus z bar. Okay, so I'll take z minus z bar squared over that cross section. Not that this is going to be different from the other integral because it is a square anyway. So finally, the torsional moment is going to be produced by shear stresses S xy prime. We're going to have to add in negative mx times z minus z bar. The mx that we want times z minus z bar. This is going to be the amount to the right based on how up we are. That'll produce a negative one, and that's why we have the negative sign there, over the integral of rc squared from y is 0 to L and z is 0 to L. And then we'll have Sxz prime is positive this based on the y position and the same integral in the denominator. So this is going to give 4 functions, 2 of which we have to add to our x stress to get the bending moments that we wanted. Those are produced by x stress distributions that depend on y and z. And the other 2 of which we have to add to our y and z stresses. So this should have no net stress as a check when they're centered on the centroid. So when you put in y is a half and z is a half, they all give you 0. So that seems like it's working. And now we can figure out what the displacements will be in our total setup for y and z here. And let's see, counting everything, we figured out earlier. Did I rerun this after putting the moment back in? Let's check. No, I did not. Okay, good thing. I ran that again. So we have a W total, which is almost 1e minus 7, and we've got about that in flex as well. What about the y displacement? The y displacement total is almost 4e minus 8, and we've got a fair bit. Oh, wait a minute, I rounded that really terribly. So it's 3e minus 8, and we've got about that as well. but the x displacement is now way off, right? We had previously only almost a third of this displacement, but now we've increased it, and oh wait, it's in the other direction too. The x displacement is negative. What's going on there? Well, maybe this is from the bending, right? Let's figure out what the x displacement is at the center of the tip. So we'll report this at Lx and Ly over 2, Lz over 2. And that one is back to the x displacement we were picturing before. We can plot, let's make a contour plot of the x displacement over the x equals Lx surface. I guess we don't really need these plots anymore. And look at that. At the corner we ended up calculating, it is bending in a lot. So there's from that moment applied on the end, not from the twisting, but from the bending deformation, we have a big difference in what the x displacement is. And this is a cube. That makes sense, right? We were calculating how much it's going to be moving transverse, but the size scale that we're at on a cube shape is also moving it back into the page. We can check that that goes away if we leave the twisting producing stresses there, but get rid of the bending producing stresses. Aha! Interesting. It's not totally due to that bending. So the hypothesis is not correct. Look at this. We still have some bending, something going in after we got rid of the extra stress that was producing bending. Where's this coming from then? This is from some warping of the surface. So from the stresses and strains that we're applying from the twisting moment, we're getting this warping in showing up. How do we do that? Maybe we'll put things in so that it's just the twisting moment. We'll get rid of this 300. I like commenting stuff out instead of deleting it. So let's put plus 300, plus 400, and we'll just comment those out. Yeah. Interesting. So it's some kind of a combination effect of those different factors. We now have a U displacement at the center that mostly matches the top. When we got rid of the shear that was showing up, with the twisting, the shear ends up making a big difference to those x displacements. Was that there before? What about before we put in the twisting? So this is just from the shear. I didn't notice that. But actually, just applying those shear forces, right, those shears are causing bending themselves. So there's some bending produced by the net shear forces on these surfaces, and that is leading to a displacement in the x direction, and modifying what we calculated before for the x displacement. So the analysis worked pretty well, except for the second order effects that we ignored when we came up with a lot of this analysis stuff. The fact that bending can lead to some longitudinal displacement as well as transverse displacement. I think this shows pretty well a lot of the reason why you want to have an analytical understanding and know how to use these calculations to figure out how things are working. It's not that doing this stuff is the way you're necessarily going to calculate it when you have access to finite element methods. It's that it's so easy to make a mistake in setting things up and not know when it's not calculating what you want it to, that having this analytical understanding for how it works in simple idealized cases and how things are going to scale is essential for getting some intuition around how these problems work. These are so difficult that you just need to do the analytical stuff. Even if you're never going to actually calculate things using these methods just to try to get a handle on what's happening in these deformations and what these things mean. So hopefully that is fun. This concludes the elasticity part. I had a lot of fun doing this. I hope you've enjoyed it. I'll see you next time, and thanks for watching.